Welcome, everyone, to the 43rd episode of Covalent Academy, Tackling Miniaturization Challenges. I'll be handing things off to Dr. Naohiko Kawasaki in just a couple minutes after some housekeeping things to share. Q&A questions can be submitted anytime through the Q&A tool, which can be opened at the bottom of your Zoom screen. After this talk, we'll be sharing both the recording and slides, more on how to access that later. Now, just a few words about covalent metrology. Covalent is a next-gen analytical services platform and lab headquartered in the heart of Silicon Valley. We provide high-quality data and actionable insights to accelerate R&D in advanced materials and devices. In addition to our over 50-plus cloud integrated and cutting-edge tools in-house, we also partner with over a dozen global leaders in analysis instrumentation, as well as 40 qualified service labs to offer comprehensive testing solutions through flexible business models. To give you an idea of Covalent's range of services, this slide captures some of our most popular techniques across different categories of analysis. Just a reminder, we'll be sharing these slides after the talk so that you can peruse these in more detail. Toray Research Center is an affiliated company of the chemical manufacturer Toray Industries. Established in 1978 and founded upon its analytical division, now TRC has 4,000 clients outside of Toray, and it is one of the best analytical service companies in Japan, providing state-of-the-art techniques based on abundant experience in physical analysis for over 45 years. The mission of TRC is to contribute to research and development in the industrial sector. Utilizing advanced analytical techniques, TRC has worked alongside clients to solve their challenges. Covalent and Toray Research Center have entered an exclusive strategic partnership to strengthen their offerings and better serve their customers. For North American customers, this uniquely opens access to the world-class resource of expertise in analytical technology. By working with Covalent, customers have a convenient channel to set up and manage their projects, leveraging the full range of capabilities of Covalent and Toray Research Center. This positions Covalent as a partner of choice for material characterization and material research, with a portfolio of solutions that is unmatched in North America. With that, it is my great pleasure to introduce today's speaker, Dr. Naohiko Kawasaki. Naohiko Kawasaki is a manager of the electron microscopy analysis team at Toray Research Center. After earning a master's degree in engineering from Tokyo University in 2003, he joined TRC and has specialized in STEM-based spectroscopy analysis, particularly electron energy loss spectroscopy for advanced electronic devices. He also contributed to catholuminescence development at University Paris Sud in 2014 and earned his PhD in science from Kyoto University in 2020. Known for his academic contributions and extensive knowledge in nanophysics, he works closely with clients to help solve technical challenges. Dr. Naohiko, I'll let you take it away.
Okay, thank you very much for introduction. I'd like to share my screen, so please wait for a while. Okay, thank you for the introduction. I am Naohiko Kawasaki from Toray Research Center, Japan. Today I'm happy to have such a nice opportunity. In my presentation, I'd like to show you the importance of the high spatial resolution physical analysis for the electronic packaging. Okay, let's start from the introduction of my talk. Electronic packaging is a techniques for sending electrical signal from outside to IC chip. In this figure shows a conventional type wire bonding type electronic package. In this structure, the signal from outside is sent to the IC chip through the solder ball, package substrate, and wire. Even in this structure, there is several kind of bonding interface. such as bonding interface between wire and IC chip, and between wire and substrate and solder board. For all the case, the interface dimension, the size of interface has an order of 100 micrometer order. Lower figure shows the recently widely used flip chip bonding structure. In this structure, a wire is replaced to this kind of bump. Then finally, the package size can be reduced compared to the previous wire bonding structure. Even in this case, the bump size dimension is almost several tens of micrometer order. So for the conventional type of electronic packaging, the required analytical physical analysis technique also has micrometer spatial resolution. So I like to show you some example data. In this example, we like to focus on here the wire bonding interface between wire and IC chip. We can see the wire bonding position from outside by using X-ray microscope. Then we cut the sample here. We fabricated cross-sectional sample here. Then the right side is optical microscope image of the cross-sectional plane. SEM-based EBSD is a useful technique to characterize crystal grain size and orientation with a micrometer spatial resolution. Generally speaking, smaller crystal grain size means greater strength in metals because dislocation cannot move freely due to the many number of crystal grain boundary. So in this sample around here, gold wire part has a smaller crystal grain size. So we can also say that in this sample, the gold wire has greater strength. On the other hand, let's see the CAM map in right side of this slide. Then CAM map means the crystal orientation difference is surrounding pixel in this experimental data. Then in generally speaking, the large CAM value means plastic deformation. In this example, in this sample, around here, the basis of wire bonding has greater value of CAM value. So in this sample, the basis of the wire bonding should be tightly connected to the IC chip, thanks to the plastic deformation. So EBSD is very useful technique to get information about material strengths through the crystal grain size and orientations. Okay, let's see the next example. In this example, we like to focus on here a bump. A bump is located between the IC chip and the substrate. Then in this sample, bump is consisting of the many number of alloys, many kinds of alloys, intermetallic compounds. So in this case, it is difficult to identify each phase by using only EDX or only EBSD. So in this case, by the combination of EDX and EBSD, accurate phase assignment is possible. Then we can also get the crystal orientation map of one phase. Even in this case, this sample has the bump thickness is also 50 or 60 micrometer order. So in this case, SEM-based EBSD and EDX with a spatial resolution of micrometer order is very useful. Then It is also important to it's also important to measure to evaluate IC chip itself. So Raman spectroscopy is very useful to evaluate stress in semiconductor. In this example, before packaging, the silicon substrate has a low magnitude of the stress, but after putting mold resin, the silicon substrate shows the large degree of the compressive strain. So by using Raman spectroscopy, we can get information about the effect of mold resin to the IC chip with the spatial resolution of also micrometer order. It is also important to find analysis of poor adhesion or peeling problem. In this upper part example, we like to consider the adhesion strengths between SAS and epoxy resin. Then, before cleaning of the SAS surface, the sample has, after cleaning the surface, the adhesion strengths become much better than before cleaning. Then we examine the surface of SAS by using TOF SIMS technique. Then we detected these kind of organic impurities before the cleaning of the cleaning at the surface. These organic impurity is very small amount, but this impurity can be a cause of poor adhesion or peeling problem. In lower parts, we like to consider the adhesion strengths between metal plate and epoxy resin. In this case, in case of aluminum, the adhesion strength is better than nickel. Then we examine the surface of metal plate by using FTIR measurement. Then in case of aluminum, we could detect OH group at the surface of the aluminum. But there is no significant functional group at the surface of the nickel. Then the OH group at the surface of the aluminum can make hydrogen bonding with epoxy resin. So adhesion strength between aluminum and the epoxy resin should be greater than in case of nickel. So I mean, we used many kind of analytical techniques to evaluate electronic packaging. So now let's see the recent trend of semiconductor devices. In this slide, I show the typical figure of the front-end process. As you know well, recently widely used FinFET is widely used in advanced front-end process. Then as a next generation, gate-all-around structure is widely studied by many researchers. In both cases, the typical unit is already below 10 nanometer. So I think it is difficult to achieve dramatic miniaturization from now in downscaling. So I mean, front-end process is almost facing the physical limit of the downscaling. So many people try to achieve the miniaturization in back-end process. Then I showed the figure of flip chip bonding again. Then conventionally, the one chip is packaged one by one. A chip is packaged one by one. But in the next generation, two-dimensional packaging, IC chip and another IC chip is connected to the directly through the interposer and redistribution layer. Redistribution layer means a kind of metal interconnect, fine pitch metal interconnect fabricated by front-end process technique. Then typical dimension is below 10 micrometer. Then another idea is to stack several chips three-dimensionally. Then even in this case, a microbump typical unit size is below 10 micrometer. Then bumpless 3D-dimensional packaging is hybrid bonding. I showed some example of cross-sectional image here. In this image sensor chip and the driving circuit chip is connected directly. Then in right side is a little bit magnified image of the different structure. In this figure, the patterned SiO2 and copper patterned sample is connected directly. So then in this case, the patterned structure has the dimension of nanometer order. So I mean, the next generation two-dimensional and three-dimensional packaging, there are a lot of interfaces in one volume unit compared to previous structure of electronic packaging. So the role of interface become more and more important compared to the conventional structure. Then interface is localized in the pattern sample. So it is also important to evaluate interface with high spatial resolution analytical techniques. So today I'd like to show some typical example. Then the first one is direct observation of the annealing effect using in-situ TM observation. In this topic, we like to focus on here. Here is just the interface between bump and IC chip. Here is a kind of metal layer. The under bump metal is here. Then in this test sample has structure, nickel, palladium, and gold multi-stack structures. And then generally speaking, the adhesion strength and electric property can be improved by annealing. So here we try to understand the mechanism of this improvement using our in-situ TM measurement techniques. Then in this technique, at first we fabricated the thin lamellar specimen for TM observation. Then we put this lamellar specimen on this kind of MEMS chip on the top of the TM specimen holder. Then we can put heat to the lamellar specimen. Then we can also put voltage to the thin lamellar specimen. If we put the thin lamellar specimen as illustrated in this figure. So let's see the experimental results. This is the result of the just heating, just annealing. Then let's see the movie. From the room temperature, then we put heat to the thin lamellar specimen. Then maybe you can see the crystallization of palladium layer. Okay, let's see again. Then around 8 minutes, the palladium layer start to crystallize suddenly. Yes, so palladium layer is crystallized. So palladium layer is crystallized at the temperature of 340 degrees. Elemental composition distribution can be also examined by using the conventional STEM-EELS techniques before and after annealing. Now, after annealing, we can confirm that nickel is diffused to the palladium layer, and palladium is also diffused into the gold layer. This metal diffusion can be confirmed in this line profile. Then after heating, nickel is diffused to the palladium layer, and palladium is also diffused to the gold layer. Okay. Then, as the next step, we try to examine the change of electric resistivity by using thin lamellar specimen in TEM. So in this case, we also fabricate thin lamellar specimen. Then we put voltage between gold and nickel. Then this graph means the change of electric resistivity between gold and nickel. Then in this case, we keep the sample temperature at 350 degrees. Then just after putting heat, the electric resistivity increased quickly by the effect of phonon scattering. But by keeping the temperature at 350 degrees, electric resistivity is decreasing gradually. Then finally, then after going back to the room temperature, resistivity is lower than initial state. Okay, so in this experiment, we could detect the change of electric resistivity during heating inside TEM. So okay, I'd like to summarize this topic. We could experimentally detect the crystallization of palladium layer and metal diffusion and electroresistivity improvement in this sample in TEM. So we can say that the adhesion strength and electric resistivity can be improved by the crystallization of palladium layer and metal diffusion. And we can also say that in this case, optimized annealing temperature is around 350 degrees. Okay, then let's go to the next topic. The next topic is a direct observation of the kappa and kappa hybrid bonding interface. As I explained before, the bumpless three-dimensional packaging is a hybrid bonding. Then, sorry. The many researchers said, many researchers predict the initial state, the surface of kappa consisting of the nanocrystals. Then after heating, the crystal grain size of nanocrystal become larger and larger, then diffuse into each side. Then finally, kappa and kappa is tightly bounded. But nobody see this kind of phenomena in real time. So here, we also like to propose our in-situ TEM measurement techniques to understand the kappa and kappa hybrid bonding mechanism. So here we also prepared cross-sectional thin lamellar specimen regarding kappa and kappa hybrid bonding. But in this case, we fabricated this cross-sectional sample from the commercial devices. So I mean, we used commercial device. So this sample is already tightly bounded. But as a test measurement, we put heat to this thin lamellar specimen. This sample is already tightly bounded in the initial state. So after heating, it is not so easy to find the clear difference, but by checking carefully to this kind of cross-sectional image, we can find the kappa diffusion from the lower part to upper part, and upper to lower. Then we also like to use this technique to evaluate grain size and orientation. ACOM-TEM techniques. ACOM-TEM means automated crystal orientation mapping techniques. In this technique, we also use small focused electron beam in TEM Then this small focused beam is scanned on the sample. Then during scanning, we got these kind of electron diffraction patterns. Then after the acquisition by the sequential electron diffraction patterns, we can calculate this kind of crystal orientation map. We can also calculate grain size quantitatively. So, I mean, this information is almost same as SEM-based EBSD, but this technique is based on TM, so this technique has a much better spatial resolution. In this case, ACOM-TM has around 2 nanometer spatial resolution. It is necessary to evaluate nanocrystals. Then we also use this technique to the kappa and kappa hybrid bonding samples. Before heating, we can see the crystal grain boundary as shown by the yellow arrow. Then some of them disappear after heating. Then we can also calculate grain size. Before heating, the grain size was 340 nanometer, but after heating, grain size is become larger, 440 nanometer. So I believe, so this technique, in-situ heating TM combined with ACOM TM is very useful technique to understand hybrid bonding mechanism. So we like to propose this technique to know the mechanism of hybrid bonding, kappa and kappa hybrid bonding. Okay. Then let's go to my final topic. Final topic is poor adhesion or poor electric reliability problem at the kappa and polyimide interface. I also explained before two-dimensional packaging. In this structure, IC chip and another IC chip is connected directly through the interposer and redistribution layer. Then, as I said, redistribution layer is a metallic interconnect fabricated by front-end process technique. Then the dimension is below several micrometer order, so it's a very complicated structure. There are several kinds of interposer: silicon interposer, glass interposer, and organic interposer. Then organic interposer has strong points. Then in case of organic interposer, we can fabricate in lower cost. Then transmission loss is also lower than other type. Then this is organic interposer, so this interposer has higher flexibility. But in case of organic interposer, it is difficult to fabricate fine pitch interconnect because insulation reliability is low. And sometimes adhesion with copper has a problem. So it is important to find a root cause of this issue. Then now we try to find the root cause of this issue by using our detailed physical analysis technique. This is a test sample of this case. This case, the distribution layer metallic interconnect is copper. Then dielectrics is polyimide. Then kappa interconnect width and pitch is 5 micrometer in this sample. So, sorry. Then this sample has a problem, the adhesion problem between kappa and polyimide. But this sample has already patterned structure, so it is difficult to use macroscopic analytical techniques. So we try to find the cause of poor adhesion problem by using high-resolution analytical techniques. Then at first, we examined the elemental distribution using conventional STEM-EELS technique. Then we can find higher nitrogen intensity around the interface between copper and polyimide at the both of the upper surface of copper and the side edge of the copper. But this case, STEM-EELS shows elemental composition distribution, but we cannot get any information from these results because EDX is just elemental composition analysis. So as a next step, we use this technique, electron energy law spectroscopy. This technique is also based on TM, scanning TM, so spatial resolution is also 1 or 2 nanometer. In this technique, we detect how large energy the incident electron beam loses. Then in the process, the inner shell core electron in the sample is excited to the unoccupied band. Then incident electron beam loses this energy. Okay. Then this excitation energy is depending on the kind of element. So by using the electron energy loss yield spectra, we can get information about elemental composition. Then not only the elemental composition, the peak structure is affected by the density of state of conduction band. So I mean, by checking the peak structure, we can also get the information about bonding structure. Then we can get these kind of information with 1 or 2 nanometer spatial resolution. Then we got EELS experimental data from the same sample. Even in EELS spectra, EELS two-dimensional map, we can find nitrogen has much intensity around the interface between polyimide and copper. Then let's see the bonding structure by using peak structure. Then at first, let's see the copper peak structure. Then area 4 means the inner part of copper. The area 3 means just the interface between copper and polyimide. Then area 4 shows the pure metallic copper, but the peak structure of area 3 is much different with the inner part of copper. Then this peak structure shows the copper oxide. Then we can also find the intensity, copper intensity inside polyimide around here. Around here means area 2. Then in area 2, peak structure is almost same as area 3. So even inside polyimide, copper is diffused, then diffused copper is oxidized. Then next, let's see the carbon and nitrogen peak structure. Then area 1 means inside the polyimide. Then area 2 means around the interface between copper and polyimide. Then here is 2 kind of peak, pi and sigma we can see. Then in area 1, inner part of polyimide, sigma peak intensity is much higher than pi peak intensity. But in area 2 around the interface, the peak intensity of pi and sigma is almost same. Then tendency is almost similar in the nitrogen KH. In area 2, close to the interface, pi peak intensity is higher than area 1. So this kind of high intensity of pi peak means there is a double bond or triple bond between carbon and nitrogen atom. So by using these experimental results, we speculated the chemical structure of the interfacial layer. This is original chemical state of the polyimide. Then interfacial layer, this polyimide structure should be decomposed. Then there is this kind of double bond. Then around the interface layer, copper is diffused. Then copper is oxidized here. So oxygen in polyimide is should be stored by copper ion. So finally, this triple bonding should be created. So in this case, we think the root cause is the copper diffusion from copper oxide. Then a polyimide structure is decomposed. Then finally, double or triple bond between carbon and nitrogen atoms can be created. So this, we think this is the cause of poor adhesion at copper and polyimide. Then to know the more detailed chemical structure, we try to use this technique, AFM-IR. In this technique, IR infrared laser is irradiated to the specimen. Then thermal expansion of the sample is detected by the needle-like cantilever. Then finally, we can get localized IR absorption spectra. In right side, in this example, the sample is phase-separated polymer alloy, then with the order of 200 nanometer order. Then these IR spectra can resolve the two phases very clearly. So we try to use this technique to get the sequential spectra using same sample, kappa and polyimide interface. Then we got sequential spectra from A to C. The A means around the interface with kappa. The C means inner part of polyimide. Then here is a sequential spectra from A to C. So here is it is difficult to find a clear difference among them. But if we plot the intensity of this wave number, the intensity is high at around the interface with kappa, then this intensity is decreasing with the distance from the interface. Then this wave number means this kind of chemical structure. So we can also say that in this experimental result, we can also say that polyimide structure is decomposed, destroyed. So this structure has COOH. This functional group is easily bounded, easily connected to the kappa ion. So we think the root cause is also kappa ion diffusion from kappa oxide. Then emitter ring is open. Then this kind of structure is generated. So this functional group is connected, can be connected to the kappa ion. So this graph shows, we think this graph shows the kappa diffusion length. Then kappa diffusion length in this case is around 1.7 micrometer order. Then this sample, in this sample, the kappa interconnect and the kappa interconnect pitch is 5 micrometer order. So in this case, diffusion length has not so big problem, but the pitch of the kappa interconnect become narrower, smaller. This diffusion length may have the problem regarding electric failure. Then finally, let me introduce our new experimental system. We will introduce a new experimental system regarding AFM-IR. In current system, the spatial resolution is around 100 nanometer order. So in this spatial resolution, it was not so easy. It was difficult to detect this interfacial layer because the thickness of this interfacial layer is around 50 nanometer. It can be detected by EELS, but it was difficult to detect by our conventional AFM-IR techniques. But our new AFM-IR experimental system is better spatial resolution, below 30 nanometer. So I believe we can get information about the thin interfacial layer. Okay. So finally, I'd like to summarize my talk. Today in my presentation, I showed several examples of high-resolution analytical techniques. Then in-situ TM combined with EDX or ACOM TM is very useful to understand the mechanism of adhesion strength, electric resistivity improvement in underbump metal. Or it is also useful, it should be also useful to understand the mechanism of copper and copper hybrid bonding. Then in the third topics, we showed electron energy loss spectroscopy and AFM-IR we used to find the root cause of poor adhesion or low electric reliability with the copper and polyimide. So I believe this kind of our advanced technique is more and more important for the next generation electronic packaging. Okay, thank you very much for your attention.
Thank you, Naohiko, for putting together such an informative overview. First off, I hope this presentation gave you a sense of just how much you can really do with high-resolution interface analysis. If you might need help with high-resolution interface analysis, or if you want to discuss a potential future project, we're offering free discovery consultations with Covalent experts. You can schedule your appointment through the link in the chat now. As we noted earlier, if you would like to reference or review these slides or presentation later, you'll be able to access all the materials for this episode and all of our episodes at academy.covalentmetrology.com. One last note before we get started on the Q&A session, you'll see a super quick poll popping up on your screen here. If you could answer these couple of questions, it helps our team to connect you with more useful, high-quality content in these talks. And with that, let's get started on the Q&A.
Thank you, Dr. Naohiko, for the very cool talk. You walked us through some really cool imaging capabilities and data. Just looking at the questions here. I've got a question. Have you analyzed polymer samples with TEM? Other than the polyimide data that you showed, any sort of cryo-cutting capabilities?
Okay. Yes, we have experienced to examine to analyze the other kind of polymer. But in case of TM, we have to be careful to make a thin laminar specimen because usually we use the FYB techniques to prepare thin laminar specimen. But in case of FYB, it is easily chemical structure can be easily broken. So in this case, we almost always use cryo FYB in cooling temperature.
Got it. Very cool. In regards to the copper polyimide interface adhesion problem, based on this data, what do you think was the real root cause? You showed that in the AFM-IR that there is some copper diffusion into the polyimide, but have you looked at the decomposition of the polyimide?
Yeah. Let's share my screen again. Yes. Yes, experimentally we could detect the kappa diffusion and polyimide chemical structure decomposition. Okay, so now we think the root cause of poor adhesion is diffusion of kappa, because how to say, all the literature also said by the kappa diffusion from the kappa oxide surface layer, a kind of void can be created at the surface of the kappa. Then, yeah.
Interesting.
Yeah. So, because the kappa ion diffusion velocity is much higher in case of kappa oxide compared to pure kappa.
Mm-hmm.
So, if we suppress the, how to say, if we can remove the surface kappa oxide layer, maybe kappa diffusion we can also suppress. So maybe this is the solution of this peeling problem, the suppress or removal of kappa oxide layer. I believe so.
Interesting. Let's see. You showed a few cases of in situ heating capabilities, essentially to understand adhesion of the solder. Are you able to correlate any of this thermal data with bulk thermal properties or other properties of the original device at TRC?
Okay. Yeah, it is always this is always a problem because as you know, in case of TM, we have to prepare thin laminar specimen. So it is the situation is always different from the original sample structure. Okay, so we have to be careful every time. Then generally speaking, in case of in-situ TM measurement, we prepare the laminar specimen as thick as possible. Then, then from the first measurement, for example, sometimes we can find how to say some kind of elemental diffusion along the thin laminar specimen surface. Okay, so in that case, this is not so good. Because original sample has such kind of surface, because the original sample is not thin laminar specimen. So if we can find the diffusion along the surface, sometimes we put protect layer on the thin laminar specimen. So in that so as these cases, we have to be careful.
Interesting. You showed us some Raman results of a silicon chip under compressive stress.
Yeah.
If you had, say, device structures that were much smaller, say on tens of nanometer scale, are there any techniques to probe stress at these length scales?
Okay. In nanometer scale Raman measurement. Okay. Okay. Let's share my screen again. We also have this technique, Snom-Raman techniques. In this case, we also use this kind of needle-like probe. Then this probe has this kind of small holes, okay, at the tip of the needle-like probe. Then we put light from the surface of the needle. Then penetrated light through this hole we use as a incident beam. So finally, we could get Raman spectroscopy with a resolution of 100 nanometer order. I think this technique is useful to characterize localized stress in the semiconductor.
Mhm. Very cool. I think we have time for one last question.
Okay.
You showed some crystal orientation maps with the AFM-TEM
Hmm.
technique. That was the before and after heating of the copper-copper bonding.
Yeah. Mm.
But you also showed some in-situ heating capabilities. I was wondering if you could combine these two and actually see what the videos look like during annealing.
Okay. In case of ACOM TM, it is possible to use during heating, but in case of two-dimensional ACOM TM map, it takes maybe several minutes to take one image. So in that case, we have to make the reaction velocity lower than usual condition. But we can get experimental data during heating. But in case of EDX, it is not so easy. It is difficult because the EDX detector should be very close to the sample. So by the emitted gas or something during heating, the ADX detector should receive the kind of damage. So in case of EDX, it is a little bit difficult. So in my presentation, we show the EDX data before and after heating. So regarding elemental composition analysis, EELS is also useful. In case of EELS, a detector is far from the sample. So EELS can be combined with in-situ heating TM analysis.
Okay, very interesting. Well, thank you very much. I think that's all the questions that we have for right now. Carissa, I'll take it back to you.
Thank you, Austin. Thank you all for joining today. And thank you again, Naohiko, for talking to us and sharing your knowledge with us. We hope it was informative and of value for everybody. Have a great day.